Good afternoon and welcome to the fourth probe introductory lecture. Let's see. Yeah. So probe is a cost action, and there are 38 cost members that are participating in it. And probe stands for profiling the atmospheric boundary layer at a European scale, and it's a 4-year cost action, and we're in the middle of it at the moment. Now, the motivation for probe is that the atmospheric boundary layer is the single most important undersampled part of the atmosphere. And this observational gap is especially important for meteorology, air quality, aviation, and renewable energy. The top priority atmospheric variables that are currently not adequately measured are wind profiles, temperature and humidity profiles in cloudy areas, and cloud profiles. Now, the challenge of probe is to look at how we can close this atmospheric boundary layer observational gap efficiently and cost effectively at the European scale. And the work is divided into 4 working groups. And the lecture that we are having today is a part of working group 2 on advanced atmospheric boundary layer profiling. So we're not just looking at doing measurements in the boundary layer, but also making high-level products that makes the observations more useful to the users. Now, there have already been 3 introductory lectures this year. We started with one on instruments for profiling the atmospheric boundary layer. And then in May, we had a lecture on ground-based remote sensing instrument networks. And then in October, we had part 1 of the high-quality atmospheric boundary layer observations. And all these past lectures, they are available on the Probe YouTube channel. And the presentations, the slides, that is to say, are on the Probe website user space for those that are users. Now, today we're looking at the second part of the high-quality atmospheric boundary layer observations. So today we're looking at indices, both forecast indices, fog alerts, icing alerts, and atmospheric boundary layer height and classification. So we have 4 lectures today. Maria Toporov is going to start with forecast indices. And then Jean-François Ribaud is going to talk about fog alerts. Ewan O'Connor is then going to take over with icing alerts. And then in the end, Juan Antonio Bravo Aranda is going to talk about atmospheric boundary height and characterization. The talk should be about 12 minutes. So we are aiming at having time for 1 or 2 questions after each talk. But then we'll have 20 minutes for discussions in the end all together. Now we have a pad, and Henri has put the link in the chat. And we recommend that if you have questions that come along while the talks are going, that you write them down in the pad, write your name, and then the question. And we will then take it up in the end, and possibly the lecturers can go after they finished and reply to it in the pad itself. If you can't do it in the pad for some reason, go to the chat tool, of course, but we'll try to limit that because it's easier to preserve the questions that go into the pad. And then, of course, when there are questions, use the raise hand to ask questions. So ask everyone to mute their microphones, except Maria, who is going to start with her talk now on forecast indices. So I think Simone is now going to give her the right to change the slides.
Yeah, I have it. Okay, thanks. I will change to the arrow. Right. No. Yes. Good afternoon. My name is Maria Toporov. I'm working at the University of Cologne, and today I will talk about forecast or stability indices. Stability is an important, but that was too fast. Stability is an important characteristic of the atmosphere that determines the tendency of the air to rise, or in opposite, to resist vertical motion. The knowledge of atmospheric stability is important for example, forecasting of severe weather events, fog danger, and for forecast of air quality. The stability is determined by the vertical profiles of temperature and humidity, and in general, we can say that the larger the vertical temperature gradient, the more unstable are atmospheric conditions. So in operational weather forecasting, stability is, or forecast indices can be used to describe atmospheric stability with a single value. And this value is typically calculated as a difference between temperature and humidity measures at different pressure levels. Here you see examples for 3 stability indices. K index is dependent on the conditions in the layer between 850 and 500 hectopascal. Lifted index is determined as the difference between the temperature at 500 hectopascal and the temperature of an air parcel which has been lifted from the surface dry adiabatically to lifting condensation level and then moist adiabatically to 500 hectopascal. In this case, shown on the right-hand side, the lifted index would be negative, what indicates the very unstable conditions. And the last one is a CAPE. It's a well-known index that gives the convective available potential energy of an air parcel that has been lifted from the surface to level of free convection. Each index has an empirical determined threshold that divides all cases into stable and unstable. In case the measured index exceeds or falls below the threshold, the potential for convection initiation or for thunderstorm or for fog is given. So different indices are developed for different geographical regions, and also it can be the threshold can vary and be different in winter and in summer. So some experience is needed to effectively apply these indices in the forecasting. Usually these radio sound ascents are used to calculate stability indices. And here on the right-hand side, you see a set of indices which are routinely calculated from each radio sound launch. However, the temporal resolution of radio sound launches is not sufficient to capture fast, small-scale, fast-evolving small-scale convective processes. And therefore, on the other hand side, atmospheric profiles obtained from ground-based profilers can also be used for calculation of stability indices. Studies were performed to demonstrate the capability of different sensors. Here you see 2 examples for atmospheric emitted radiance interferometer and for microwave radiometer. And these 2 time series show the typical summertime case in which convection starts to develop after the sunrise and generate thunderstorms in the afternoon, which are shown with black lines. The increasing values of K index and CAPE correspond to increasing instability and can be well measured by microwave radiometer, which is shown with blue line. But looking on the radio sound values only, the forecaster, which are shown with red dots, the forecaster would have missed this rapid increase in instability. The accuracy of such product is dependent on the type of retrieval applied to microwave radiometer observations. But in general, it could be shown this MWR provide forecast indices with correlation above 0.8 compared to radio sounds. On the other hand side, the ground-based profilers provide only a single point observations, which are representative only for some area around the observation location. But this information is not sufficient to create a map of forecast indices, which can be helpful for operational weather forecasters. A more complete picture provides satellite sensors. Here you see an example for global instability index products that is based on severe observations. Image shows K index. We see that this product is restricted to cloud-free areas, and cloud are shown with gray scale. since the observations are performed in infrared. As the next image below, it shows the CAPE index over US calculated from combined infrared and microwave observations from polar orbiting satellite. The combination with microwave makes atmospheric profiling possible under cloudy conditions. However, even these temperature and humidity profiles have low accuracy close to the surface, especially in the boundary layer, which is so important for calculation of CAPE index. So if these lower humidity values in these profiles are replaced by surface measured in situ measured humidity values from ground-based from surface network, and CAPE index calculated from this modified profiles, we see that resulting CAPE fields reveals much higher CAPE values over east part of US. These examples show that satellite observations are not sufficient for capturing atmospheric conditions, atmospheric stability, and that these observations can also benefit from additional ground-based measurements. So in our work at the University of Cologne, we address the questions: in what extent can ground-based profilers complement satellite observations and improve assessment of atmospheric stability? We performed theoretical experiments based on reanalysis as truth and simulated observations from satellite and for ground-based sensors, and developed a neural network retrieval of 7 stability indices. I will show the results for 4 sensors. The first 2 are satellite sensors. First is a SEVIRI, broadband SEVIRI, which is operational in geostationary orbit. The second one is a, infrared sounder. It's a hyperspectral sensor, which will be launched probably in 2024. And the ground-based sensors are microwave radiometer and dial. Both ground-based sensors were already introduced by Pauline Martinet in the previous lecture, probe lecture. From the observational point of view, all indices can be divided in 3 groups. The first group includes indices which are not dependent on surface properties. And the indices in second and third group are lightly or highly dependent on the temperature and humidity in the boundary layer, or especially highly dependent on these properties close to the surface. Therefore, it can be expected that satellite sensors would well measure the indices from the first and second group, but will have difficulties to capture CAPE, Fox-red, and convective inhibition. So we developed a retrieval and applied it to 7 years of simulated observations of SEVIRI, infrared sounder, microwave radiometer, and for combined ground-based sensors, microwave plus dial. Here you see the probability of detection of unstable convective events for 7 indices. And as we can see, I will focus on infrared sounder and microwave radiometer, shown in green and yellow, with green and yellow bars. As we can see that single IRS and microwave radiometer provide quite high probability of detection of 0.75. But the IRS outperforms microwave radiometer for the first 5 indices, which belong to the first 2 groups. But for 2 indices which are highly sensitive to temperature and humidity close to the surface, the microwave radiometer can outperform satellite sensor. But the results for these 2 indices are worse than for other 5. And further improvement can be achieved if we use water vapor profiles from dial sensor. If we apply synergistic retrieval, that means if we take IRS and microwave radiometer observation vector as input for neural network retrieval, we can see that this synergistic approach is beneficial for all indices. It is shown with transparent part of the bars. It's beneficial for the first 5 indices, but for the CAPE and Fox-red, these additional ground-based observations are really essential because IRS alone is not so good. Yeah, so I won't show the results for cloudy conditions, but it could be shown that probability of detection from IRS drops down to 0.4, and that under cloudy conditions, the ground-based observations are essential and must be added to the satellite measurements. So further, here we see the example of application of the retrieval to observations simulated for the domain in the west part of Germany. And here you see the liquid water path showing cloudiness, the true CAPE, so the CAPE calculated from reanalysis. And third and fourth images show the CAPE calculated from the IRS observations and from combined IRS plus MWR observations. We see that IRS retrieval often underestimates CAPE or produces outliers, and that the synergistic retrieval performs better, but it's still not optimal. For lifted index, we see a bit different picture. We can see that under clear sky conditions, IRS performs quite well, but when clouds appear, our infrared sounder basically see clouds and cannot see the atmosphere below them. And synergistic retrieval in this case performs very well. And in this, on these images, the retrieval is applied in each point of the domain. That means we assume that we have microwave radiometer every 4 kilometers. So these images show only the accuracy of the retrieval. The next question is, how can we combine CAPE and lifted fields from IRS and with single observations from microwave radiometer or from my network of microwave radiometers? And to show the impact of additional ground-based measurements, we performed the special statistical interpolation and merged CAPE fields from obtained from IRS observations on the left-hand side with CAPE values from a network of ground-based microwave radiometers in the middle. And the weight of each source of information within this approach is dependent on the error covariance matrix of each retrieval. And in poise with available microwave radiometers, we applied a synergistic retrieval to show the best possible results. So the analysis, the error of analysis was assessed, and it could be shown that even one sensor placed in the center of the domain leads to a reduction of root mean square error of the analysis. But for the number of sensors larger than 20 or 25, no further improvement can be achieved. Now let's have a look on the application of this method to the time series. And here the fields of CAPE obtained from IRS were merged with values of CAPE obtained from 10 microwave radiometers, which were placed in the location of operational DWD stations. Here we see that the field can be improved, but the high CAPE values are still underestimated. And in case the infrared sounder provides entirely wrong field, for example here, wrong field of CAPE, this field cannot be corrected with 10 microwave radiometers. So the main problem, the main limitation of this method applied to CAPE fields poses the low accuracy of IRS retrieved fields itself, and also the high variability of CAPE index. In case of lifted index, we see that under clear sky conditions, as already said, IRS performs quite well, but when clouds appear, 10 microwave radiometers can partly correct the field of CAPE and well measure these low CAPE values, which indicate unstable conditions. And with this, I conclude that this method applied to CAPE fields shows that additional observations from ground-based network improve IRS retrieval under both clear sky and cloudy conditions, but the problem is that the retrieval is still not very accurate. So here we need further additional maybe surface in situ temperature and humidity measurements, and maybe water vapor profile from collocated dial. Or next possibility would be first to retrieve profiles, temperature and humidity profiles from both sensors, and after that calculate CAPE index. And for lifted index, the analysis were very accurate, and lifted retrieval based on IRS is more accurate than CAPE, and therefore it works better. But this retrieval is affected by clouds, and in this case, ground-based measurements can effectively replace cloud-affected IRS pixels. And I would like to thank you for your attention, and will be happy to answer your questions.
Thank you, Maria. Are there any questions for Maria? Just raise your hand in the Zoom tool. So I have one, Maria. So what's the plan onwards? Where do you see this going?
Actually, I'm not working anymore on these stability indices. We try to assimilate the brightness temperature measured by microwave radiometer directly into Icing model, and in this way to show the impact of microwave radiometers.
Okay, thank you. Any other questions? If not currently, feel free to write it in the pad, and we will.
I think someone has a question.
Is there a question? Yeah, Juan Antonio.
Yes. Hi, thank you. I was always wondering about the representativity of the stability indexes determined with the macro radiometer. So if we have these values, they represent few kilometers around the instrument, or it can reach hundreds of kilometers around.
That is the same as for radio sound launches. Yes. But it can be assessed maybe from reanalysis by calculating the covariance between different points. Yeah, that was not assessed in these experiments because I used the covariance matrices from retrievals and not the covariance matrices of CAPE from reanalysis. So, but it's always different and depends on on the orography and geographic locations.
Okay, thank you.
Okay, thank you, Maria. Before we go on, can I ask everyone to go over to the pad when they have a minute and register as a participant? That would be really nice. Thank you. The next one up is Jean-François Ribaud, and he's going to talk about fog alerts.
Hi everyone, do you hear me? I think so. Today, yes, I'm Jean-François Ribaud from IPSL. So today I'm gonna present you what you can expect in terms of alerts when you have a foggy situation. So about the context, the first question is what is fog? And according to WMO, fog occurs when the visibility at the Earth's surface is lower than 1 kilometer, and that should be due to the presence of suspended water droplets. So it exists several types of fog, like radiation, stratus lowering fog, advection, freezing, precipitation fog, and so on. But today we will mainly focus on radiation and stratus lowering fog, which are the most common continental fog. So the second question is why fog needs to be monitored and forecasted. And on the map on the right, you can see the hours per year of low visibility at different European airports. And it's easy to see that the number of hours is quite significant. And as a consequence, fog may be responsible of several disruptions at airports, but also may cause road accidents. And for all these reasons, fog is hazardous and needs to be monitored and forecasted. So the challenge to forecast, so the classical approach relies on numerical weather prediction model, but we know today that they usually struggle to reproduce the timing of the fog onset, its spread, its depth, and liquid water pass. And this is due, in fact, to complex surface-atmosphere interaction in the boundary layer. And for coarser grid models, we have parameterization issues, whereas for limited area models, it's more about boundary condition problem. The other possibility is to use ground-based observations that may provide valuable key information. So first, to monitor specific physical processes driving fog formation, but also to complement numerical weather prediction model. And they also present a very high temporal resolution, like here it means every minute. So for the ground-based observation, we have a low space resolution, but very high temporal resolution. Whereas for a numerical weather prediction model, we have a compromise with good space-time resolution. But today we will focus on ground-based observation. So here I've listed you 3 different fog retrieval algorithms. So the 2 first one on the left and the middle are based on machine learning techniques. So the first one on the left is not a prediction, it is a classification problem. Let's say you don't have any instrument, but you have webcam images on an airport or on a highway, and you would like to make a classification to know if you have a clear view or a foggy situation. So this is an algorithm developed by Martin Régnier in Belgium. And on the middle, the other machine learning technique is regression. So it means we have a prediction model. So this is based on visibility, weather station observation, and ARC measurement. And here they try to predict different range of visibility for lead times of 30 minutes to 2 hours. So this is an algorithm developed by Philipp Knellinger at University of Innsbruck in Austria. And on the right, you can see the Parafog tool that we will focus on for the rest of the presentation. So Parafog is able to retrieve different levels of alert in near real time to support nowcasting of fog formation. And you can see here like moderate and high alert several hours before the fog onset here on the right. But I will explain you in detail now. Oh, so Parafog tool is developed at CIRTA Observatory in Paris since 2015 and is experimentally used at different French airports. It is based on automatic LiDAR ceilometer, so IRC measurement, visibility, and classical meteorological information with a time resolution of 1 minute. It provides pre-fog alert every minute, indicating the risk of the fog formation, and it allows also to discriminate between radiation and stratus lowering fog types. So right now, Parafog is calibrating using 9 years of measurement at CIRTA Observatory in Paris and 1 or 2 fog seasons at 5 different European airports. So just about the methodology, Parafog just use all the input with a time resolution of 1 minute, and then we have 3 different steps. So the first step, we check the relative humidity. If this value is higher than 85%, Parafog is turned on. And then we check the visibility. If the visibility is higher than 1 kilometer, it means that we have a fog formation risk. And then we derive the cloud fraction from ALC measurement. And we use the cloud fraction to make a discrimination between the stratus lowering fog formation or radiation fog formation. And you can see that for both radiation and stratus lowering fog formation modules, Parafog is able to retrieve the same alert level. So we have low, moderate, and high alerts. So here just two radiation case studies. So on the left, you have a sick radiation fog event at the Sirta Observatory, whereas on the right, you have a thin radiation fog event at Munich Airport. I think I don't have time to go into detail for each panel, but we will focus here on panel F for the sick radiation fog event at the Sirta. So you can see the ALC measurement from the bottom to 400 meter above. And you can see that the fog event here will start close to 2 a.m. in the morning. So you have the alert that Parafog is able to retrieve on panel G. So the fog is correspond to violet, the color violet. And just before this fog onset, you can see different color like yellow, orange, and red colors, which means we have low, moderate, and high alert that occur here quite, let's say, 90 minutes before the fog event. On the right, we have quite the same layout, but you can see here on panel E that from ALC measurement that we have a very low values and low signals. So we have a very thin and patchy fog. And you can see that before the event in violet, we have again different color like yellow, orange, and red, which means we have low, moderate, and high alert a few minutes before. Just also two examples of stratus lowering case studies. On the left at the Sirta Observatory, on the right at the Zurich Airport. So you can see from ALC measurement, very nice stratus here on the left or on the right, here on the panel E, fluctuating few hundred meters above the ground during couples of hours. And you can see that again, Parafog is able to retrieve the different alert level before the fog events. So it was just perfect cases to show you what you can expect, but we did also quantitative assessment of Parafog performance about radiation fog and stratus lowering fog. And we know that for both fog types, the hit rate is almost 100%, which means that Parafog do not almost miss any event. And the false alarm ratio is about 10% for radiation fog, whereas it represents 30% for the stratus lowering fog. So just to conclude, we have encouraging results from quantitative assessment that attest quite good performance of Parafog. So for all of this, it warrants now an extended application at European scale via the probe cost action now and the e-profile network. And for that, we had a sub-working group meeting 2 weeks ago, and we define a proposal, like a process for probe site team interested in using Parafog. So first we will test and run Parafog based on 1 month of data to see if everything is fine. And then we will implement near real-time version for the site interested. Like on the right, you can see the official website of Parafog with the 4 different sites in near real time, but we can easily add a new site. So we know that we have already countries already interested by using Parafog, like in Slovenia, Belgium, France, but maybe you are also interested. So please don't be shy. You can contact us. I think, yes, that's it. And if you have questions, I would be pleased to answer them.
Thank you very much. That was really interesting. Are there any questions for Jean-François? If not,
Hello.
I'll start with, is there a question?
Yes.
Yes.
I'm Flori Toanca from Romania. I would like to ask if it's possible to use the Luftceilometer in place of Vaisala.
So for the Luftceilometer, you are talking about the CHM 15K. That's right.
Yes.
Yeah, I think it's quite complicated because close to the surface where we have the fog processes, we have an overlap, and to monitor this particular fog processes is quite difficult. So we will miss this part, and for this reason, I would say it's not possible. So it's possible with Vaisala CL31, CL51, but with the Luftceilometer, it would be complicated. But maybe Simon has more information about that, but I think this is an overlap problem.
Yuan, did you have a question?
I agree with this assessment. I think it's maybe something that could be tested because the signal also from the CHM is better when you have very strong scattering from the aerosols that are swollen. So if you have more humidity, so right before the fog, it could be that you get a good signal. But as far as I understand, you also need some reference observations earlier when you don't have so much humidity. So this could be challenging with the local sensors due to this overlap issue that was mentioned by Jean-François.
So,
okay, so this is Ewan. I just had a question. What's the minimum set of instruments that you would need for this?
To run Parafog, you know?
Yeah.
Yeah, so we need ALC measurement like from CL31 and relative humidity from a weather station and visibility from a scatterometer. That's the three different instruments, the minimum configuration.
I mean, you can add more instruments if you want, but that's the minimum that you need.
Yes.
Okay.
It's very doable.
Exactly.
I think we should carry on to the next lecture. And that's actually Ewan. Ewan O'Connor, and he's going to talk about icing alerts.
Okay, I have control now, I think. Is that right? Let's have a look. Yes, I do. Okay. So, hi everyone. My name's Ewan O'Connor, and I'm from the Finnish Meteorological Institute in Helsinki, Finland. I'm going to talk to you about icing alerts. First question is, why are they important? Well, they're important for two main reasons. There's many others as well, but both for safety and financially. So if you think about here is some examples of the wind turbines, or this is power lines, so electricity lines. As soon as you have icing, you actually start to lose power, partly because it's not as efficient, and actually for here in the power lines, you actually start to lose. Again, the transmission is not so efficient, so over long lines, you can actually lose quite a lot of losses. And together with that, it's not just that these ice up and aren't so efficient, it's also that they can throw ice off as well. So it's just icing on turbines, masts, tall buildings, for example, as well. That's actually quite a big danger. And then if we go further up in the atmosphere, then for aircraft, it's also clearly rather dangerous as well. If we think about what we're normally thinking about is that the sort of heights we're interested in are in the boundary layer, and for aviation safety, that's because the main danger for icing is actually during takeoff and landing. At other times, they can actually figure out just how much lift they are getting, and they can deal with it a little bit. But if during takeoff and landing, you don't have as many options. So if we think about the sort of heights we're thinking about, normally I would have said below 200 meters or even 100 meters for wind energy production or electricity power lines. But we know now that actually for wind energy, even 200 meters might not be enough in the future. And the reason we think about aviation safety above 200 meters, it's normally the decision about whether to land or not is normally taken at the decision height, which is a little bit above that. But it's also if you're in a holding pattern above an airport, for example, you tend to be flying quite low, and again, you're going to be in the boundary layer. Okay, so how do you normally actually measure icing if you're working for a national weather service? You're normally using in situ observations on a mast. So here's an example of the mast on the right. You can actually have quite tall masts, maybe 200 meters, 300 meters if you're lucky. And the idea is you would have one of these types of instruments that actually sits somewhere on the mast and then can actually measure the icing. So how do they actually measure icing? I've got two examples here. One is this Guðrún icing sensor, and the idea is this particular one has this nickel alloy rod, and the point is that basically vibrate at a specific frequency, and then as ice builds up on this, the frequency as you're adding all of this ice mass, the resonant frequency obviously decreases, and that's how you measure. So you measure the frequency, and that tells you whether it's icing or not. Another one is you have this sort of instrument as well, again sitting on a mast, and the idea here is that it's sending out an ultrasonic signal, and then as the ice builds up around the edge, again the signal decreases, and you can use that to measure your icing. Okay, so one interesting, so these have actually been in use for a while. They tend to work quite well. However, there are a couple of issues with them sometimes. Is that when icing has reached a certain level, if there's a certain amount of buildup of ice, then the heater starts to automatically defrost the sensor, and now this actually means that it's not actually working. So it's not actually giving you any information while the heater is on, because obviously you're not actually measuring any icing. So you actually lose a period of time. Now, as we said before, we're actually interested in looking maybe above the height of the masts. So the point about some of these instruments can be actually mounted in, say, the nacelle of a wind turbine. So that's where the hub is. But if we've got now having these turbine blades of 80 meters or 100 meters or even more, then of course you're actually missing out quite a large part of the atmosphere that could be conducive to icing. So what we're thinking about here, so again, obviously one of our favorite instruments, we're talking about automatic LiDAR and ceilometer, so ALC, which is typically used for cloud aerosol profiling. And the point about using this for icing is that we're actually interested in identifying supercooled liquid layers, which are the ones that are most responsible for icing conditions. And I'll show you that a little bit later. And the idea is all we need to do is if we can identify the cloud base and we have some sort of temperature profile, then we can actually identify these supercooled liquid layers, and then we have our icing potential. Now, of course, what we can also do is identify if we actually have other types of cloud as well, so it's mixed phased ice, snow, for example. It's possible to do freezing, drizzle, or rain, but I wouldn't be as confident with that at the moment. So what are the advantages of using an ALC to actually do some icing detection? Well, we've got relatively dense networks. You don't have to go up and mount them on the mast. Again, automatic operation in all weather conditions, just about. And now we're no longer limited to mast height, although we are actually limited to the first cloud base normally. And again, they also don't suffer from this heating problem, where obviously once there's a certain amount of ice is accumulated, then you don't get any measurements for a while until we've got rid of all the ice. Okay, so how would we actually go about this? Again, so if we actually think about, here's an example of about 24 hours of attenuated backscatter from a ALC somewhere. So what we tend to do is, because we've been dealing with aircraft people, so aviation safety, they want everything in feet. Well, actually, they want it in flight levels, but that's directly from feet. And then this is the sort of height in kilometers, which we're a bit more used to. The idea is we can identify the liquid layers here from the attenuated backscatter coefficient. So for those of you who are used to it, it's rather obvious by eye, but then you can actually need an algorithm to detect that. But the idea is these red layers here, here, and here, for example, we can identify as cloud. And then if they're cold enough, then we know that they must be supercooled cloud. Okay, so rather than just saying, oh, it's easy to do this, there is actually a method done by Mintu Tuonanen, who actually used basically generated a mechanism for identifying liquid layers, which wasn't dependent really so much on the absolute value, but had a little bit more look at the shape and a few other bits, and could also identify fog as well at the same time. And the advantage of this was that you didn't need your instrument to be perfectly calibrated, so the use of thresholds isn't so strict for this particular method of detecting liquid clouds. Okay, so if we take this example here, we found some clouds, and then we actually know the temperature from a numerical weather prediction model. And then what we do is to try and simplify this for the forecasters who then are talking to the airports. We can then just simplify this into a few classes. So we've got freezing liquid or likely freezing liquid, or just normal cold precipitation, i.e. ice or snow, is in red. And then we can actually also do warm liquid and warm precipitation, or nothing detected, i.e. of course there's aerosol there if we go back in this bit, but as far as the icing algorithm is concerned, we don't see anything there. Okay, so that's what we want to give to the forecast, is something quite simple, and we can identify our liquid and precipitation, and then we say wherever we have the supercooled liquid cloud, that's where we expect the most icing to happen. Okay, so we say it's supercooled liquid cloud rather than precipitation. Okay, so why is the dark red more likely to be icing than the precipitation? Because some people think tend to think of it must be the snow that's causing precipitation. What we actually have is we have a mast similar to this at the same location, and what we have is at the top of it we have one icing detector halfway up the mast at about 100 meters, and we have another one at the top of the mast at 270 meters, and that's the one in blue. And what we have here is the ice formation rate as measured by the in situ sensor sitting on the mast. And you can see that if we're thinking about 272, the cloud base is around about 250. So the higher icing detector is in clouds, and the lower one is only in the precipitation. And then what you can see is actually the icing rate for the in cloud one is much higher than the one that's only in precipitation. So it's not that there's no icing from the precipitation, but it's not as much as in the supercooled liquid cloud. Okay, so that's why we're using the ceilometer, because that's easy to give us the cloud locations, and then the temperature tells us it's supercooled. Okay, so now we can confirm that supercooled liquid water is responsible for most of the icing that we see. And of course, we can still detect the precipitation as well, and then we can still say there might be some icing from that. Okay, eventually what we were doing for this particular work is to see whether or not the model forecast of icing was any good. And it turns out actually the model, at least in these locations, wasn't bad at all. So what we have on the bottom plot here is output from the model. Okay, so the resolution is hourly, so it's not 30 seconds or 1 minute in the way of the ceilometer is. But again, in principle, you can see that the icing rate, which is basically a measure of, it's actually taken from the supercooled liquid water in the model and the wind speed in the model. This is the icing rate calculated, and you can see that actually it's suggesting there's icing at more or less the same sort of locations as we actually observe the clouds. And you can even see it even has this higher level one up here, which actually corresponds to where we can see it occasionally actually in the observations. So actually this means that in principle, where we don't have observations, we can also have a good idea whether or not the model is likely to be good in specific cases or not. Okay, and then what we're trying to do is is this operational yet? It's not quite operational, but we did a test where we set up a few sites that also had in situ measurements as well. And this was run as part of a matinee project for FMI together with aviation forecasters. And the idea is we're trying to present them some reasonably simple form of icing alerts, so they could actually have a look at what the observations were showing, and they could have a look at the model at the same time. And here you can see this is an example where there's a front comes through and it goes from warm to cold. Okay, and actually you can see the icing rate from the model actually seems to be rather well actually with what we think we're seeing in the observations. And again, you can see even in this case, actually the icing rate from the model isn't too bad in this particular case. Okay, so this is what we tend to show for the forecasters. It's quite a simple view. If you wanted to, we can also go a little bit further and actually provide all of the other observations as well. so we can provide a lot more information for those who are interested. And here you can even include the actual observations at the same time as well. So this is actually just the temperatures on the mast, and here we actually have the icing rate on the mast as well. So you can see that these actually agree rather well with what we are actually suggesting is coming from the ceilometer observation. So no icing for the first part of the day, but potential for icing later on in the day. Okay, so that implies that we can actually even do model verification. I don't want to go into this too much, just to show you that we are just beginning our work on this. And Guðrún, Hämäläinen, and others have actually done a little bit of work on this as well, where we're looking at how good the model is at actually predicting icing. And here's some examples here. So if we're thinking about the sort of skill scores we want, if we're looking at bias, you want a bias value close to 1. And we see that actually nearly most of the observations and the model predictions are actually agree really well, up to, say, the first maybe 500 meters or so. What I should say is the different colors tell you whether or not it's a coastal station, inland station, or Lapland station. And that's important for us, obviously. And what you notice is actually the coastal locations are the ones that aren't as good. And this is the blue one in many of these skill scores, whereas the inland stations and the other stations are actually quite good. So this is suggesting that the model doesn't do quite so well over the sea as it does over land for getting particularly low clouds. And then some other things that we can also say is that because we have a lot of low clouds in Finland, then some of the scores do tend to decrease as we go up in altitude, mainly because this is actually the observation problem, and it's not really a problem with the model. It's because we're limited to the first cloud base, and then we can't really tell you anything about what's going on above that. But in principle, this means that we can actually go and verify the model predictions as well. And then that means we can actually get a good indication of whether the model forecast or the model prediction is going to be good enough for, say, a few hours ahead or not. Okay, so where could this be applied? Well, in principle, wherever there's an ALC that's producing attenuated backscatter profiles. So you can actually see that this is a few hundred, maybe about 400 or more across Europe. So we can apply this at any station. All we need is a ceilometer, and we need some output from a numerical weather prediction model. And the good thing is this can be applied to almost all ALCs, and calibration is not crucial for this, so it doesn't have to be perfectly calibrated, because we're looking at strong signals, so because the clouds provide a very strong signal, and it doesn't have to be perfectly calibrated. So that's what we're interested in here. Okay, so in principle, we can apply this to anywhere in Europe. Of course, not everywhere is interested in it close to the surface, but maybe higher up still might be important for aviation. Okay, the other good thing is icing alerts are actually very quick to generate. We just need the ALC profiles in time and the model temperature profile, so we can do that at many locations, and we can basically produce this within a few seconds of actually getting the data in. So that's quite fast. We have evaluated this with the in-situ measurements, and it's quite clear that it really is the supercool liquid water that dominates the icing conditions. And we can also show that we can start to test the model forecasts and have a look at things like the skill scores and the climatology and bias at particular sites. Okay, thank you very much. Are there any questions?
Thank you, Johan. The questions for Johan?
I have actually a question.
Yes.
To Johan for the presentation. So if I understand correctly, you don't have a lot of requirements for the ASC quality, or it's just you need the profile of attenuated backscatter. And does it require a lot of the processing that you do to generate the alerts is also not very intense, I understand.
No, it's not too heavy. The easiest ones are clouds which are above the ground. I mean, obviously the ceilometer is designed for giving you cloud base, so that's why it's quite easy to do. But what Turunen had done is that we can also include a little bit better discrimination between the precipitation and other things. So then we have the precipitation as well. And the other one was actually being able to identify fog, at least in the Vaisala CL31, CL51 as well, because what we're using here is the profile shape rather than a threshold value. So that's why we're not so sensitive to the calibration. But obviously, if you're thinking about clouds, fog is quite difficult because the first gate is already quite high. So we had an extra thing to look for that.
So, I mean, this is a very promising tool, I assume. Are you discussing applications along over this large network that you showed with all the different ceilometers?
I would like to chat to Rolf about this, if somewhere like even eProfile would be interested. For us, the issue for us was actually getting we were trying to get the model data. That's not too bad. But then we're also trying to generate the icing rate from the model to then be able to show the icing rates that as well, because that's what the forecasters want. And that's the one thing that might be a little bit extra. But the actual icing potential alert is very quick.
Very nice, thank you.
So I have one question, Johan. So have you been giving this to the forecasters at FMI? Have they been using this?
Yes, some have. Again, it's yet another bit of information, and they are overwhelmed with information. So that's why we try to keep it as simple as possible. But yet, certain sites, especially those, I think it's the aviation people, aviation forecasters are interested in this. So, yeah, so
you're getting positive feedback.
Yes, the only problem is, well, the only time I tend to know that there's positive feedback is when I get the negative feedback because the site isn't running. So
yeah, well, when people complain, it's because they're using stuff.
Yes, exactly.
So that's good. Okay, I think we should carry on. Thank you, Johan. So we have the last talk of this this lecture, and that's Juan Antonio Bravo Aranda, and he's gonna be talking about ABL heights and characterization.
Okay, thank you so much. Let's see if this works. Okay, that's it. This is the outline of the talk. Despite its topic is interesting enough for a speech of more than 30 minutes, I'll try to give some key concepts of each part of it. And then, okay. This is, first of all, we need the definition of the ABL. Among the different definitions we have, I've chosen this one agreed within the cost action to prove. But just as summary, we can just keep in mind that the ABL is the lowermost layer of the atmosphere affected by the surface in a time scale of hours. The ABL is quite important because in many research fields, among them, I highlight the air quality, since ABL is where the contaminants are diluted, as we can see here. Let me check, here it is. So, for example, the ABL top height used to be lower during the nighttime than during the daytime, and thus pollution concentration is expected to be larger during nighttime, since they are dispersed in larger volume during the noon. No? So this is why the ABL can be so important in air quality. So, again, okay. So the ABL is mainly a matter of turbulence, which can be mechanical or thermodynamic. Here we have, obviously we can have both or none in the ABL. The mechanical turbulence is linked to the wind shear, and the thermodynamic one is linked to the vertical temperature gradient. The power supply of the ABL turbulence is mainly the sun. So paying attention of this idealized daily evolution of the ABL, we find that first the sun hits the surface, and then the thermodynamic turbulence starts. As solar energy increases, turbulence also increase, reaching like the maximum of the ABL during the day. since this is the also named mixing boundary layer or convective boundary layer. Then when with the sunset, the radiative cooling start to cool the surface, and then also the sphere, the lowermost part of this atmosphere, because causing a temperature inversion, which this kills the turbulence, the convection, no? Then the turbulence slowly disappear in the ABL. And finally, the region that was previously the convective boundary layer become neutral with a neutral instability, and can have also mechanical turbulence inside. With time, this residual layer can be stratified. Then let's see. Okay. Here we have the evolution of the reconnected signal of a ceilometer, and that can be understood as a proxy of the aerosol particle concentration. We can see that the idealized evolution of the ABL can be found more or less in this real measurement. The first aim of to characterize the ABL is to detect its top height, that can be here in this edge. So we can use the signature of the ABL in the particle concentration with height. So firstly, we will have this high concentration in aerosol, and then abruptly decrease to nothing of aerosol. So the ABL height can be determined using this kind of changes in the atmosphere. So if we explore the ABL with different instruments, we will obtain different signature depending on the different properties that we measure. For example, we have here the virtual potential temperature, the standard deviation of the vertical wind speed, the concentration of aerosol particles, and the horizontal wind speed also. These are the profile representing this profile B within the daily evolution. Then we can see here, it's work. Okay, here it is. So if we check each one of these profiles, we can see that we have like sharp changes of the profile, then that can be used to determine where is the ABL top height at this part. Okay. But to do so, we need like vertical result profile of each of these quantities. So we need instrument to do so. If we go according to the moment of the day, or simply because we have different, we don't have this idealized evolution or profile, but real measurements, we may have more than one. More than one change in the profile with height. For example, here we have this change because of the interface between the stable boundary layer and the residual layer, and we have also this change from the residual layer to the phytosphere. So now the question is not where is the ABL top height, but which one is the top height. So we have several candidates, and then we need a method to choose which one is the ABL top height. When we have this convection starting, then the situation is a little bit more complicated, because we may have different signature from different atmospheric properties. For example, we start with the virtual potential temperature. We can use this value to check the maximum height reached by an air parcel rise from the surface. This point that's here doesn't mean that the air parcel has reached this point already when we launch, for example, the radio zone. This height is like a forecast. The maximum height that this parcel will reach in height. So this is like the future from it can be seen as future. I'm sorry, I forgot this point there. So we have this area parcel here, which rise up to here. So this is the potential maximum height that can reach this air parcel. The instability causes turbulence. Watching the standard deviation of the vertical wind speed as a fingerprint of the turbulence, here is where we see the convection right in this moment. No? So this is exactly up to this height is where we have this turbulence. So it's like exactly the current situation of the convection. Then we jump to the aerosol concentration. So the turbulence causes this mixture of the aerosol. So it is a matter of time that this aerosol mixing becomes homogeneous. So up to here, then we have this decrease, and then it starts the residual layer and then the phytosphere. So this kind of jump is due to this instability, and it's the consequence of the instability that was highlighted by the virtual temperature. So therefore, we should expect like a different location of the convective boundary layer depending on the atmospheric property that we use. So here I explain the partial method that, as I said before, is the temperature, the virtual potential temperature in the surface found again in the vertical, and this can be performed using both micro radiometer and radio zones. And we can also use the aerosol concentration, and which is this profile, which is idealized. For obtaining this profile, we can use the backscatter LiDAR and accelerometers, and that is what we have in this quick loop. No, so in black we have the resoelectric signal, and the wavelet covariant transform. It's like a mathematical tool to highlight where we have these kind of changes in the profile in the profile. But the issue in these cases is that we may have different local maxima in the profile. So which one is the correct one? Because if we can see the quick loop by eye, we can say this is the correct point of the ABL top height. But if we want to do it automatically without checking the profile, without checking the quick loop, then we have to set sorry. So if we check these different wavelets with time to determine where is the ABL height, we have to set a threshold. So for example, we can say that the ABL height is the first local maximum of the wavelet covariance transform of the RCS larger than a given threshold. No, so it would be, so this one is a, sorry, now this one is the maximum the largest local maxima, and this should be lower. So the threshold should be something like here. This complicates the use of this method to determine the ABL height. We have also different algorithms like the KABAM developed by Simon Kothaus. In this case, we determine like different candidates to be ABL, and then there's an algorithm to discard some of the candidates. For example, this one is this one is an artifact caused by the instrument, so it's removed in this step. So applying different conditions, then we obtain the final ABL height evolution. But the layer attribution may fail under given situations such as a dust outbreak. These are 3 days. Yeah, it's like 3 days evolution of the race quality signal, and we can see in pink the wavelet covariance transform, the ABL height determined with the wavelet covariance transform, and the gray triangles are the ABL height according to the macro radiometer. And we can see here how the wavelet method determined as ABL the top of the dust layer, which is not indeed the final ABL. We can see more clear here in this picture where we have the race quality signal, and here below the parallel to perpendicular RCS ratio. Here we have largest value which are linked to the dust layer, and here below the atmospheric boundary layer. So this the polarization can be used to determine where is more or less the interface between the ABL and the dust layer. This method is Polaris, and it uses the wavelet covariance transform applied to the polarization ratio. And also we have we can use the standard deviation of the vertical wind speed determined with the Doppler lidar that can be used to determine the total kinetic energy dissipation rate. That can be seen here in this quick look from the paper 199 et al. 2018. With these values, we can determine the ABL, but not only the ABL height, but we can characterize the different sublayers within the ABL, which is the next step. So the idea is not only characterize where is the ABL top height, but identify the different sublayers within. For example, this is the decision tree used for each pixel to decide if it is within the ABL, if it's convective, if we have wind shear, or we have both. It's like intermittent region, and this is and it's also the skewness of the velocity, vertical velocity is also used to determine if convection is driven by the surface or by clouds, which is also an important step in this kind of ABL characterization. And I think that's all from my side, because this, yeah, exactly. Yeah, exactly. Thank you for your attention.
Thank you, Juan Antonio. Any questions for Juan? If there are no direct questions for Juan Antonio, we can open the floor for any questions and just start the discussions in general. Just raise your hand or write your name in the chat. Juan Antonio, you want to start?
Yes. I have a question for you, Juan, because I don't know if we can use this Icing alert with the ceilometer we have in Granada. Granada is like 20 kilometers away from Sierra Nevada mountains. So I don't know if we can use the information from Granada to check if we may have or not icing in the Sierra Nevada mountains.
Good question. Also knowing a little bit about what the winds are like around your station as well, after chatting to Pablo. If it's stratiform, cloud, probably it would be okay, I think. I mean, so the conditions that you would normally get icing would be stratiform liquid cloud.
Okay.
So then it's just a case of whether or not the temperature profile from a model in Granada is good enough. So,
thank you.
I guess you and we would have more problems in Iceland using this, as a lot of the icing episodes are wet snow icing and not in cloud icing. I guess the ceilometers wouldn't do much.
Nor will you still be able to detect that it's snow. So, and then it's a case of, if you know how much snow and what the wind is like, then that would also indicate the potential for icing. So that's why we include the precipitation. We try to have the precipitation classification as well. Yeah, so at the moment we're really designed for what we expect in Finland, but I suspect there will be some, other bits that we'd need to add.
Yeah, we have this interesting situation in Iceland, is that when you have icing events on power lines, it's usually in the highlands. And usually the response is to put them in the ground afterwards, which means that you don't get any icing after that.
That's also happening in the north here as well. There's a lot more power lines going underground now, both for wind reasons, but also for icing reasons.
So I think the questions in the past have already been answered. I'm guessing if Jean-François, if you want to talk a little bit about the question from Luca about the best instruments to use.
Yes. So the best instrumental setup to use Parafog now is the Vaisala CL31 with the Toporov firmware, or the CL51. And we already had the discussion about the Luftceilometer, so the CHM15K. So I'm not an expert at all of the CHM15K, but I think that the first range gates will probably of poor quality due to incomplete overlap. So that might be a very hard challenge for Parafog in order to correctly monitor fog processes. And also Parafog needs to have a reference profile a few hours before the fog. So it's probably a very hard challenge for Parafog to use CHM15K. So definitively use Vaisala right now.
Yes, I found it very interesting in your talk to see, how far in advance some of the medium fog alerts were coming in.
Yeah, so we consider 3 different alert levels, like low, moderate, and high. But what we assess about Parafog performance is about the high alert, which is the highest alert we have. But for the person that use the Parafog, you should consider the low and moderate alerts, like to first alert to be okay. You have to pay attention to the situation. We are now close to foggy situation, and that's the idea. But the overall assessment of Parafog is on the high alert.
Simone, do you have a question?
Yes, I would like to ask Juan Antonio. Thank you very much for the nice presentation. Just if you could give a few words on the topic of the comparability between the different products. So you showed that we have so many different sensors and methods that are able to retrieve the heights of the boundary layer and the mixed layer. Where do you see the role of probe in advancing these products, and what are the next steps that we need to take?
Well, from my point of view, the next step is the full characterization of the ABL. I mean, to determine the stable boundary layer, the residual layer, and the complex boundary layer, as the Manning method, and also Kabam, I think, does something similar. And I would say that the next step is also to fill the gap that we have between the in situ measurements, for example, with towers that reach up to 200 meters, and then from this 200 meters to, for example, the 1 kilometer, where the genoptic ceilometer reaches the full overlap height. So we have there like a gap between the 200 meters and 1 kilometer that we need to focus on this. And also this is linked to the very beginning of the convective boundary layer. I don't know if I can show the evolution of the ABL, but say at the very beginning where the ABL start to grow, I think we have there quite important issue. Exactly, here it is in the very beginning. We have this birth of the ABL. Exactly this part, exactly where it is now, the pointer. I think we may have some difficulty, and even lower, because probably, I don't know the scale of this height, but yeah, it's something like what's happening between 100 meters and 1 kilometer. I think this is the region where I would like to focus now on the research.
Thank you. And I think it's also important to stress that the different the variety of sensors that we have to monitor the boundary layer heights give us often complementary information. So if we combine different sensors or technologies, we start to better understand this topic that you mentioned, that you get different information if you use temperature or aerosol profiling. Yeah, it's true that in I also did it, but we are used to see papers when they compare, for example, the ABL height from temperature, and other one from aerosol concentration, or for example also the LiDAR Doppler, which measure really turbulence, and they try to compare them like if they are all the same. But indeed we can see that maybe in some moments of the day they are not the same. So we have to keep this in mind and try to make this full picture of these different atmospheric variables. Yeah, exactly. Thank you.
Sven Erik, you had a question?
Yeah, I was typing it down now. This is Juan Guantanio, because I would like to hear about his considerations about the difference in this of the stable boundary layer between the aerosol layer height and the mixing height and the turbulent, the height of the turbulent layer. What are your considerations during stable conditions?
Yeah, this is a good question, because the stable boundary layer used to be not so stable because of wind shear. So we may have this mechanical turbulence near to surface during nighttime. Luckily, for example, in city center or big cities, like for example in Paris, we can see that the stable boundary layer is really affected by mechanical turbulence and so on. So for the stable boundary layer, I used to see that people use like the temperature inversion height, like the top of the temperature inversion height, using the macro radiometer to distinguish this from the residual layer. I don't know if this answers your question exactly.
Oh, not really, but that's okay. And then I have an additional question, because you were talking about the mixing height, but I mean, there is on the top of the convective boundary layer, there is a quite deep entrainment zone. It can typically be 20% of the height of the mixing layer. So you cannot predict the mixing height with a very high accuracy. You must define it inside the entrainment zone.
Yeah,
do you understand what I ask?
Yes, we used to point that the mixing boundary layer is something. Maybe if we can check the yeah, but I mean this yellow zone is like to try to highlight this entrainment zone, and the mixing height could be something like can be set in the middle of this entrainment zone.
Okay, thank you.
Any more questions? Any of the lecturers? You and Damien had a really nice question about the difference in time resolution.
Yes, I mean that is a bit of an issue, Damian.
Yes, I saw your answer, but actually, so you have every hour measurements of the temperature from the model, not measurements, actually, it's output from the numerical model, and the backscatter signal for the ACL. So did you take into the account, for example, the wind speed? I mean, I think probably it have some dependence on the icing, the wind speed, or I don't know.
No, so for what we're looking at from the oscillometer measurements is just to detect the potential for icing, and then we can have a look, and if the model actually has the cloud at the right point, then the model actually then predicts the amount of icing, which does take into account the model wind speed. I think the other point that you did bring up, which was good, is that obviously we have to have a temperature profile from somewhere, and the temperature profile might not be perfect, especially if you've got something like a frontal system coming across. You can have quite rapid change in the temperature profile. Although for many icing events, I won't say all, it's a relatively stratiform situation quite often. So that means that at least the temperature isn't varying so much. Of course, if you've got stable layers, then whether the model gets those right is a question that Sven Erik would ask, but it's somewhere to start. So that's why what we do is we identify the liquid and then show both the warm and the cold, and then that means that the forecaster at least can then say, well, if I think the temperature is wrong, then I can assume that this bit might also be icing, or if the temperature is colder than it should be, then they can actually say, well, this might actually not be causing icing in this situation. So at least we can identify the locations where it can happen, and then that gives the forecaster more information.
So actually, you look for the liquids above the zero isotherm, for example.
That's what we're looking for. Yes.
Okay. Thank you.
Okay, I think we've actually run out of time. So I think the only thing left is actually to thank the lecturers for very interesting talks on different topics. So thank you very much. So thank you all for listening and participating in the discussion, and have a good night.